Hello everyone, today I make a video about our new progress on RWKV-8 ROSA, Beyond Attention. I'm Hao Wen from Guangdong Laboratory of Artificial Intelligence and Digital Economy. Okay, let's start. Why we need a new architecture? Actually, it's because the training time scaling law is hitting a wall and it becomes ineffective. This is not said by me, it's said by Ilya. And also Ilya recently has a new video about this one. Okay, this is not my topic, so let's go forward. Scaling up model size and data size leads to diminishing marginal returns. Research on test time scaling become a hot topic today, and the efficient issue of transformer is amplified here. So new architectures offers new potentials to solve both problems simultaneously. And first, let's look at the limitation of full attention. Is full attention all you need? Actually, no. There are two main challenges of full attention. One is quadratic time complexity. The computational cost of long sequence training and profiling is substantial due to the quadratic time complexity. So make it a significant bottleneck in practice. Second, the linear space-time complexity. Linear space complexity. This is the size of KV cache increasing linear with the decoding length will cause OOM errors. And at the bottom, we have a figure which shows the inference complexity and the training complexity of RWKV, and you can see RWKV has a O1 inference time complexity and space complexity, and has an ON training time complexity and memory complexity. People try to go beyond full attention, and one of the solutions is called linear attention. What is a linear attention? Actually, the linear attention is hardware efficient model RNNs. Linear attention equal linear RNN plus matrix valued hidden states. There are two key features in linear attention. One is matrix valued hidden states. Previous work previous RNN like LSTM and GRU, they has a vector valued hidden state. So here is one key difference. Another key difference is previous RNN we say the traditional RNN is normally non-linear RNN like LSTM, GRU, all of them are non-linear RNNs. Okay, so let's say how the states update. The most simple way is we have a vector of value and a vector of key, and we will do an outer product. And this two vector outer product we will get a matrix, and then we sum up the matrix, we will get our new state ST. Okay, so this is the most basic idea of linear attention. So there are too many updates of this basic version. The first one is RWKV-6 and also member 2. Another one we call it test time online learning is RWKV-7 or other work like DataNet. And here is a figure about RWKV-7. This shows how we design the transitional matrix here. So we can get a better transition from ST-1 to ST. Okay, more about RWKV-7 you can watch my video here. I provide the link at the bottom. Okay, so we go forward. Today our topic is what's the advantages of linear attention, especially RWKV-7 here? Actually, we found it's especially good at large bench size inference. RWKV-7 can run very large bench size inference. So this maybe makes some difference, like in the reinforcement learning. If you have a larger rollouts, you will have a better result. So for RWKV-7, we can try very large rollout number. Yeah, we are still do experiment about this, so we don't know yet, but we think it's very promising. Okay, here is a demo to show how we run 350 bench size on a single customer GPU. I think it's a 9019 or 5019. Yeah, and it can achieve 5,000 tokens per second. Okay, finally we come to our today's topic. Why we need a new architecture beyond RWKV-7? Because some people observe, yeah, actually the meta-analysis paper from Google Research observe all current recurrent models only shift the curve and the slope is unchanged. What does this mean? This means all of this new architecture compared to multi-head attention, they have a better performance when the sequence length is small, and when we go to long sequence, actually the performance becomes worse and worse, and the slope has a positive slope. So some work try to solve this and only shift the curve to a larger sequence length, but cannot change the slope. So our goal is flatten the slope, not just shift the curve. So we need a new mechanism which can capture long range dependency while supporting online computation. So RWKV-8 ROSA introduced an alternative algorithm based on suffix automation, yeah, to achieve linear time context modeling will preserve information. First, what is a suffix automation? A suffix automation is a compact graph that remembers all possible substring of a word. Here is the example of substring of ABCBC, and each circle here actually groups substrings with the same ending, allow fast detection of substring match in linear times. So here is the definition. Actually, for each position, find the longest repeat pattern from the past and copy the tokens that follow it before. So this algorithm helps us to find the longest matched pattern in the context. And here we give a name of this suffix automation algorithm called Rapid Online Suffix Automation. So we call it ROSA. Okay, so ROSA can dynamically construct a suffix automation, and the algorithm records the historical pattern of a sequence. When predicting the next token, it only needs to match the longest common suffix. It doesn't rely on any softmax or KV cache. Okay, here is our some result. This figure is very interesting. Yeah, this means ROSA is a parameter-free next token predictor, and we can see when we have a longer and longer sequence length, and our error become lower and lower. Why? Because longer context has a better substring matches and a lower error. Normally, naive ROSA can achieve 100% MQER and needle in a haystack. But naive ROSA is not useful for real-world tasks. So actually, we're trying to combine these two. We build a new hybrid neuro-symbolic architecture. So we're embedding ROSA in each LLM layers by this way. Yeah, we just give a embedding layer each layer, and to convert our ROSA result to embedding. And the ROSA is a symbolic root system, and LLM, especially here RWKV, is a continuous representation system. So it's a hybrid new architecture. And I think we found the embedding ROSA cannot talk to each layer. So we want to build a new system can talk for each cross layer, can can do cross-layer communication. So we invent ROSA 1-bit. And this new architecture can invent internal monologue languages. Okay, so how to train it? Yeah, embedding ROSA is easy, but for the ROSA 1-bit, how to train it? The RL style training is possible but noisy. Our goal is to find a more efficient training method. And we found a simple way here. We call it local gradient. We only have 2 words vocab, and we convert the channel to a binary thing, and compute the gradient by flopping 1 bit at a time. So this can do very fast with the vocab equal 2. So here are our early result. How we can reverse the digit from 16 digits with 99.8 accuracy with only 40 key parameters. And we also show that our new method can have a lower training loss than the embedding ROSA. And we also observe internal language invented by RWKV-8 ROSA. Yeah, these are all promising results we have now, and we want to share with the world. Okay, that's all. So takeaway is ROSA is a symbolic context propagation mechanism, offer a new paradigm beyond traditional attention. So RWKV-8 ROSA combined with LM embeddings enable modeling of long-range dependency without relying on attention. Okay, that is my today's presentation. Thank you for listening.